In this video, let's take a look at volumes of solids with known cross-sections. And in the next video, we'll take a look at revolutions. All right, so this is a pretty cool GeoGebra applet, and it's going to give us a nice visualization of what this section is about. Okay, so far we've looked at area, which is the integral of the top function minus the bottom function. So that's our two-dimensional. So this time, what if we start stacking squares and we find a three-dimensional figure? So then our figure is going to kind of come out at us. If we have one square and we have multiple squares, and let me go ahead and extend this all the way from one end of the interval to the other, sorry. And then I can add in more squares, and of course we're going to have a nice area. But if I have these squares, and let's see if I can get it to, yeah, there we go. Now you can kind of see them in a three-dimensional. Now we've got volume, all right? And we can see that, let me reduce the number of squares so we can just kind of look at one or two of them, that the area of a square would just be our side square, and the side is determined by the top minus the bottom function. And so we can find the area of each of these squares times the change in the x, and that'll give us volume. Whoops, kind of gets away from me. And the more squares, of course, the more solid the figure. Pretty cool. So we're going to look at squares. We're also going to look at equilateral triangles, nice, and semicircles. So you need to know the area of each of these shapes. All right, so let's get started. So the volume of a solid with a known cross-section perpendicular to the x-axis. That means they're going to run vertically, and this will be dx. It's going to be between some interval from A to B of the area of the cross-section times dx, and that'll give us the volume. And of course, we'll have volume of solid with known cross-sections perpendicular to the y-axis, and that's going to be from some interval from C to D, area of the cross-section dy. All right, so here's our first example, page 65 in your Cycle 3 packet. It says, find the volume of the solid if the solid lies between planes perpendicular to the x-axis at 0 and 4. So we're going to have two planes from 0 to 4, and we want to find the volume of the solid figure, and that solid figure is going to be a square, be squares. Okay, so the cross-section is perpendicular to the x-axis on the interval from 0 to 4, and these are squares whose sides run from this negative square root of x to positive square root of x. So let's go ahead and draw in our representative square. So the base of our square, and we know that squares all have the same size, so that makes it nice. Trying to draw one in here three-dimensionally. The top function, of course, is our square root of x, and the bottom function is the negative square root of x. So one side of my square is going to be the top minus the bottom, which is 2 square roots of x. And the area is going to be the side squared. So our area is going to be 2 square roots of x squared. And if I work that out, that's going to be, well, 4x. Okay, so the area of one of these sides, the area of one of these squares is going to be 4x. So my integral will be from 0, volume, 0 to 4 of our area, dx. All right, so this is pretty simple. Let's just find the antiderivative. So 4x squared over 2 evaluated from 4 to 0, and so that's just going to be 2x squared evaluated from 4 to 0, and if I plug in 4, 2 times 4 squared minus 0, so 4 squared 16 times 2 is 32 units cubed. And that would be the volume of this figure. Okay, let's take, here's the solution worked out again. I like to practice, so I got it written out there. All right, here's our next example. The solid lies between planes perpendicular to the x-axis at x equals -1. So here's the -1, and x equals 1. And so I'm looking at figures in this region, and we know that these figures are semicircles. So let's go ahead and draw a representative semicircle, so I can kind of get a visual of what I'm doing here. and this is going to be a semicircle, something like this. And so what we see is we have the diameter. Area is pi r squared divided by 2, since it's a semicircle. We're able to identify the diameter, and the diameter is going to be the top function, which is this negative quadratic, minus the bottom function, which is the just y equals x squared. It's positive quadratic. So top minus bottom is going to be 2 minus x squared minus x squared. So it's going to be 2 minus 2x squared. Okay, so this is the diameter. If we cut it in half, we'll have the radius. So if let's just divide it by 2, my radius is going to be 1 minus x squared. So now the area is pi times the radius squared divided by 2. All right, before I write up my integral, I'm going to go ahead and expand that binomial. So I've got 1 minus x squared times 1 minus x squared. And if I FOIL those together, that's going to give me 1 minus negative x squared minus 2x squareds plus x to the 4th. All right, and so my integral, my volume, is going to be from -1 to 1 of pi times the radius squared divided by 2 dx. Okay, so here is my integral equation. Let's go ahead and I'm going to bring out that pi over 2 in the front. So the volume is going to be pi over 2. And then from -1 to 1 of 1 minus 2x squared plus x to the 4th dx. If I antidifferentiate, this is going to give me x minus 2x cubed over 3 plus x to the 5th over 5. And we're going to evaluate that from 1 to -1. And so this is going to be, I'm going to change colors just so I can see my next steps here. So this is going to be pi over 2 and then times 1 minus 1/3 plus a 5th minus -1 let's see, -1 cubed is -1, so plus 2/3, and that's going to give me -1/5. And then I will distribute the negative and combine my like terms. So pi over 2, 1 minus 1/3 plus a 5th plus 1 minus 2/3 plus 1/5. Combining like terms, pi over 2, 2 minus, did I mess up? How did I get, this should be 2/3. There we go, minus 4/3. That should be a 2, not a 1/3. 4/3, and then plus 2/5. All right, common denominator. I mean, you can leave your answer like this, but if you wanted to go ahead and simplify that, a common denominator would be pi over 2, and then common denominator would be 15. So 30/15 minus 20/15 plus, how about 6/15? So 36 minus 20, I'm going to write my final answer. Let's see if I can squeeze it in up here. Pi over 2 times 36 minus 20 is 16/15. And this is units cubed. All right. Here it is again, worked out. Pi over 2 times 16/15 units cubed. Great. All right, last question. It says, let R be the region in the first quadrant bounded by the x-axis in the graphs of y equals natural log x, which is this guy here, and 5 minus x, which is this guy here, linear and a natural log. Question B says, region R is the base of a solid. For the solid, each cross-section perpendicular to the x-axis is a square. So we are going to have two integrals because we have two top functions. We have the natural log function that's going to produce a square that looks like this, three-dimensionally. And then we'll have a square over here produced by that linear function. That's going to look something like this. Write but do not evaluate an expression involving one or more integrals that gives the volume of the solid. Okay, so the other thing that we need to know is we need to know what the boundaries of each of the intervals are. We know that this first interval starts at 1 and it goes to some value here where these guys intersect. And then the second interval is going to start here and it's going to go to, it looks like 5. 1, 2, 3, 4, 5. Yeah. All right, so we do need to go to a graphing calculator to find out what this point is. We're going to call this point A comma B, and we're going to just tell the AP grader what we think the A and B values are. All right, so I've already typed the equations in just Desmos. Natural log x and 5 minus x, and if you just click on the intersection, it'll give you those coordinates. So 3.693 and 1.307. So let's take those back to our graph, and I'm going to say my A is approximately 3.693. I will show you how to store these values in your TI calculator so that we're not having to approximate. If we store the actual value, then there's not going to be any decimal errors. All right, so let's write our equation. So for part B, the volume is going to be from 1 to A, and our side is created by the natural log function on top minus the x-axis on bottom, dx. Remember, it's top minus bottom. And then we're going to add to, side squared, I almost forgot. Don't forget it's side squared. Side, so this is the length of the side, squared is the area times dx. If you leave off that squared, you're not calculating volume. All right, and then so from A to 5 is the second interval, and that's going to be 5 minus x, and let's square this minus 0. And do you need the minus 0? Probably not, but I'm just showing you that the side. Oh, and I probably should put the minus 0 in the parentheses, because I do want a side. Top minus bottom squared dx. All right, I think that solves for B. Now, part C, it says the horizontal line y equals k divides the region into 2 areas of equal area. So I'm going to erase all of this, and now we're going to divide this into 2 regions of equal area. So maybe like right here, and this is going to be y is equal to k. So this time we are going to have horizontal rectangles, and we're finding area this time, so we're not going to be squaring any sides or anything. We're just going to have a rectangle that runs horizontally. So if we want 2 different regions that are equal, I know I'm going to have 2 integrals equal to each other, okay? And so the area of the first integral is going to go from 0 to k. Remember, we're following the y-axis now. So from a y value of 0 to a y value of k will give me these areas. And if we are going to have these horizontal, then we need to solve for x, because our expressions need to be in terms of y. So I'm going to go ahead and take each of these functions, natural log x and 5 minus x, y equals 5 minus x, and solve for x. So in the first equation, I'm going to exponentiate, and so e to the y is equal to x. And in the second equation, I'm going to go ahead and add x and subtract 5, so x is going to be 5 minus y. All right, so from 0 to k, and the right function minus the left function this time. It's not top minus bottom, but right minus left. So the linear is going to be the right function, and so it's going to be 5 minus y minus e to the y dy. That's going to be the area of each of these rectangles from 0 to k. And we're setting up these equations where this area is equal. So I'm going to have an interval from k to my b value, and right minus left, it's the same equation, dy. All right, and that's how we solve this one.